Good morning, students. I am Dr. Roy, and today we are going to discuss physiology of hearing. You people have been well acquainted with the concepts concerning the anatomy of the ear, and today we'll start a new topic, that is the physiology of hearing. So, before we start a new topic, I would just like to reiterate the definition of hearing. It is a sense by which the sounds are perceived. And to add to your knowledge, what is sound? Okay, sound in the first place is produced by a combination of compression and rarefaction of the air waves that leads to production of sound. And this effect is produced on the organ of corti by a vibration of air molecules that I've already explained, or specifically by the compression and rarefactions. So then afterwards this sound travels through a certain pathway, and it is mainly the ear that receives sound waves, and this ear then later on discriminates the frequencies and transmits this information to higher systems, which is the central nervous system. We will be discussing this in more detail, but for the time being it is just an overview. Okay, so this is an example illustrating the concept of hearing. Actually, it is actually showing the conduction of sound waves from the external ear to the higher centers. So let us start from here. We start imagining that sound is produced by the compression and rarefaction waves, which in turn traverse this external auditory canal, and then they strike this tympanic membrane. Okay, so this portion of the ear is actually called the external ear and is also known as the conductive apparatus. But specifically speaking, the conductive apparatus actually terminates here at the stapediovestibular joint, where the oval window is inserting into, where the stapes foot plate is inserting into the oval window. So what happens here when the sound wave strikes the tympanic membrane? What happens that most of the sound is reflected back because of the greater surface of the tympanic membrane. But some of the sound that is transferred into the middle and then into the inner ear actually leads to appreciation of sound by the higher centers, and this is actually by a process which is known as impedance matching. But before we embark upon impedance matching, I will for the time being skip it, because in the next coming slides you will be able to have a better comprehension of this concept. But for the time being, let us know that sound can travel faster through the solid and through the air. But if the sound waves strike liquid surface, most of the sound energy is reflected back. This is what is happening in the ear, because here in the inner ear you all know that there are cochlear fluids which reflect back the energy, and so this loss of sound energy is actually compensated by impedance matching system. We also know it as the transformer action of the middle ear, right? But we will be discussing it in more detail in a few moments. Okay, but by and large, when this causes changes in the cochlear fluid, it leads to generation of electrical impulses, which then travel through the nerve fibers to the higher centers, specifically the area 41 and 42 of the auditory cortex. But now we will be discussing in detail what is the acoustic pathway. So whenever, okay, here you can appreciate this is the cochlea. So the signals that are been transmitted by the hair cells, they travel through the cochlear nerve onto the superior olivary nucleus. Okay, and from the superior olivary nucleus it goes to the lateral lemniscus, and then the inferior colliculus, and then to medial genicular body, ultimately ending up in area 41 and 42 of auditory cortex. So please remember that M is for music, and L is for light. So whenever we talk about medial genicular body, it is related to perception of sound, and lateral genicular body is actually related to, or is more concerned with, the precision of light. L is for light, M is for music. Okay, so I would like to go back to previous slide, and here I would like to make some important points about the impedance matching mechanism. And since now we have understood that there is a loss of sound energy because of presence of fluid in the ear, so nature has actually compensated for this by putting certain structures in the middle ear that converts sound which is of a lesser force to sound of a greater force, and this is accomplished through impedance matching. It is by and large, the impedance matching is concerned with the lever action of ossicles, and then hydraulic action of tympanic membrane, and lastly by the curved membrane effect. I will try to oversimplify it for you as what is the exact role of these structures. Okay, regarding the lever action of ossicles, actually it is a handle of malleus that is 1.3 times longer than the long process of incus, and thereby it produces a mechanical advantage, or it gives a mechanical advantage of 1.3 times. Secondly, the tympanic membrane area is much greater than that of the foot plate. Here you can appreciate that the tympanic membrane is much greater than the foot plate. Okay, so this also gives an mechanical advantage almost 14 times. Okay, and lastly there is a phenomenon known as curved membrane effect. What is it? The movements of tympanic membranes, here you can appreciate, they are more at the periphery as compared to the center. It is stiff and slightly tilted inwards, but therefore the movements of the tympanic membrane are more pronounced at the periphery, right? So this also provides some leverage, mechanical advantage to the amplifying the force of the sound. So overall, the force of the sound that is lost because of reflection of sound energy is then augmented because of interposition of these structures, which is in congregation known as the impedance mechanism or impedance matching system of the ear. So I believe you have a certain concept of it, and once the sound is conducted from the tympanic membrane up to the stapediovestibular joint, what happens next? There are movements of the, here you can appreciate, this is the stapes foot plate. So whenever there is movement of stapes foot plate, the sound is actually then transmitted to the cochlear fluid. I believe that you people are able to observe it. Here lies the cochlea, and this mechanical sound is then transferred to the cochlea, which is concerned with the conversion of this mechanical sound into the electrical sound. This is the major function of the cochlea. If there is damage to cochlea, patient would be able to appreciate, patient would not be able to appreciate any sort of sound, because there is no conversion of mechanical energy into the electrical energy. But in the case where there is retrocochlear, and by that I mean if there is a damage to the higher centers, anywhere from here up to the auditory cortex, the patient would be able to appreciate sound, but he would not be able to differentiate whether someone is honking or someone is talking or whatsoever is the case. But if the cochlea itself is damaged, there would be no conversion of mechanical sound into the electrical sound. So cochlea, which is the sensory portion, is mainly concerned with the conversion of electrical waves into electrical waves, and this actually happens because it sets up in motion of the basilar membrane. I hope you people are well acquainted with the anatomy of the ear. So this leads to the movement of basilar membrane, and it sets up a force, a rather type of shearing force between a tectorial membrane which lies above the hair cells and the hair cells itself. So the shearing force between the tectorial membrane and the hair cells leads to generation of electrical potential which are known as cochlear microphonics, because it is an action potential which is occurring within the cochlea and is known as cochlear microphonics. This cochlear microphonic triggers the generation of further nerve impulses. right? So then this nerve impulse travels through the acoustic pathway which I've already delineated, that is the cochlear nerve, the superior olivary nucleus, lateral lemniscus, goes through the inferior colliculus, the medial genicular body, and it ends up in the area 41 and 42 of the cortex, right? So there are two types of hair cells. I presume you people are well acquainted with that, the inner hair cells and the outer hair cells. We would just be interested in knowing the nerve supply because this is very important. Mainly inner hair cells are innervated by the auditory nerves, and this happens in 95% of the cases, and outer hair cells, they are innervated by auditory nerve, which is the case only for 5% of cases. So the major difference between two types of hair cells is that the inner hair cells, they are arranged in a single row, but outer hair cells sorry, excuse me, they are arranged in either 3 or 4 rows, and the number of hair cells, outer hair cells, exceeds that of inner hair cells. Outer hair cells are approximately 12,000 in numbers, but inner hair cells are approximately 3 to 4,000 in numbers. And outer hair cells are primarily the nerve supply of the outer hair cells is primarily efferent fibers, and there are very few afferent fibers. But for inner hair cells, primarily it is innervated by afferent fibers, and then there are very few efferent fibers. So another important thing is that the outer hair cells, they are more susceptible or more vulnerable to trauma that can happen by ototoxic drugs and sound trauma or noise trauma. But the inner hair cells are sort of more resistant to these insults, right? So the next thing that can be asked in the Viva question is the structures that are present in the internal auditory meatus. I've just penned down these here because it is very commonly, the questions are very commonly asked about the structures that traverse the internal auditory meatus. So you should know that it is actually an internal auditory meatus is actually a chamber that is divided into 4 quadrants. I've made a mnemonic for students, please commit it to your memory: 7 up and coke down. So if we divide it into 4 quadrants, it is the facial nerve that lies up, and coke down. Co is the cochlear nerve. I've written it here, the CN, which is actually representing the vestibulocochlear nerve. So the cochlear nerve actually lies in the inferior portion. So 7th nerve is occupying the superior half of the internal auditory meatus, and the vestibular nerve or the cochlear nerve, it actually lies in the inferior. The facial nerve superiorly, because it's 7 up, 7 is the facial nerve, and coke is down, the cochlear nerve is in the inferior portion. And then the vestibular nerve is further divided into 2 portions, the superior and the inferior. Here I've written it, so the rest of the 2 compartments, because internal auditory meatus was supposed to be a chamber that was having a further 4 compartment, it was further divided into 4 compartments. So it was occupied superiorly by the facial nerve and inferiorly by the cochlear nerve. And then the 2 chambers that were left behind, again, and superior chamber which was filled by superior vestibular nerve, and inferior one was occupied by inferior vestibular nerve. So I believe people are now well conversant with the physiology, and here I have shown an animation. So again, you can appreciate that sound waves, which are mechanical waves, they are collected up pinna, and then they vibrate this eardrum, they reach the ossicles, and then they stimulate the cochlear fluids. This electrical impulses, they travel to the nerve fibers and ultimately ending onto the area 41 and 42 of the auditory cortex, which are the Brodmann areas, right? This leads to appreciation of sound, and I presume this is clear to you. And now we would be discussing the mechanism of hearing. So I've already discussed what was the conductive apparatus. I'll reiterate what is the conductive apparatus. It starts from the external auditory canal, that is a pinna, and ends to the stapediovestibular joint, where the stapes foot plate is inserting into the oval window. And whenever there is a very loud sound or auditory stimulus is too loud, nature has provided a protective reflex which is known as attenuation reflex. This loud sound leads to contraction of the stapedius muscle and tensor tympani muscles, which leads to dampening of the force of the sound. right? So here I've written it. Reflex that occurs when loud sounds are transmitted through the ossicular system into the CNS. It leads to contraction of stapedius and tensor muscles so as to dampen the intensity of the sound or the force of the sound, and it is known as attenuation reflex, which is a protective reflex to protect the ear from noise trauma. Whenever a very loud sound or a sound of high intensity is presented to the ear, it leads to contraction of stapedius and tensor tympani muscles, right? And I've already discussed it, the function of the cochlea. There are two portions of the sensory system. The first is sensory and the neural pathways. Neural was concerned with the nerves which led to area 41 and 42, but for the time being, we will again reiterate what was the function of cochlea. Mechanical waves that were produced as a result of compression and rarefaction were converted into electrical impulses, specifically the cochlear microphonics, by this cochlea, and which was a result of, I'm going to again repeat why it happened, because of the shearing force between the tectorial membrane and the hair cells. It led to generation of cochlear microphonics, which traveled through the nerve fibers, specifically cochlear nerve, to the area 41 and 42 of the auditory apparatus. Then we are concerned with we are going to discuss the vestibular apparatus. Vestibular apparatus is actually concerned with maintenance of balance. So here it is written, an organ that detects sensation and is concerned with equilibrium. Yes, it is actually concerned with maintenance of balance. But the actually balance is by and large dependent on two apparatuses, that is the peripheral and the central. And among the peripherals receptors, we have the inner ear, which plays a primary role in which plays an important role in maintenance of balance. Okay, regarding the vestibular apparatus, we have a sensory organ of auricle and saccule. Before I embark upon this sensory organ, I would like to reiterate that there are three structures that are concerned with the maintenance of balance, that is the auricle, saccule and the semicircular canals. I hope that you are well conversant with these structures. Okay, so what is macula? It is the sensory organ of the auricle and saccule. Peripheral receptors are mainly of two types, as I've already discussed. They are the macula and the crista. So crista are actually located. I have already discussed that there are semicircular canals, and they have ampullated ends and non-ampullated ends. And in their ampullated ends, they have a sensory organ which is known as crista, and they are primarily concerned with the angular acceleration. And the second sensory organ, that is called macula, it is then present in the auricle and saccule, right? So these are actually the two are collectively known as the otolith organs. The macula of the auricle lies in its floor in a horizontal plane, but that of saccula lies in its medial wall in a vertical plane. So this is very important. Please bear it in mind, because this would be very important once we are going to discuss stepidotomy, because in stepidotomy we can damage this macula of the saccule, since it is lying in a medial wall, in the medial wall in a vertical plane, and whenever you are going to insert a piston, there is a likelihood that you can damage this as well. Okay, so these sensory organs, that is the macula of auricle and saccule, they sense position of head in response to gravity and linear acceleration. So just to reiterate, crista was associated with angular acceleration, and the macula was associated with detection of linear acceleration, right? Okay, I've already discussed it, but again, just to take a mental note of it. Sense of balance is modulated peripherally by three systems, that is the visual reflexes, and this constitute majority. This is very important for you, please commit it to your memory. The visual reflexes play a primary role in maintenance of balance. And then peripheral receptors, that is the vestibular receptor, and proprioceptive senses, that is the joint that are present in your that are receptors that are present in your joints. So collectively these constitute 30% of balance maintenance, but majority is dependent on visual reflexes. So this brings an end to our today's lecture. If you people have any query, please contact us on WhatsApp. Thank you.